Continuing this afternoon session is Daniel Lenz from Chemnitz, who will tell us about a uniform existence of integrated density of states for models in safety.
Okay, thank you. First of all, I should like to say that I'm very happy to give a talk here. So this is a talk on, broadly speaking, on random operators, on certain aspects of random operators, namely the integrated density of states. And it is based on joint work with other people from Chemnitz, namely there are two works. There's work of Michael Gruber, Ivan Veselic, and myself on a quantum graph version of a certain result, and that uses somehow methods we developed with Peter Müller and Ivan Veselic for the discrete graph on C to the D. And somehow it is a bit of the nature of an ergodic result or combinatorial result, and corresponding ergodic things for quasi-crystals have been developed together with Peter Stallman. So we kind of use, we are inspired by what is done there. So the outline of my lecture is as follows. So plan. So first, I'll give a little introduction in the type of models we are interested in. And that will be completely non-rigorous. And then I'll speak a bit about the setting, and there I will give precise versions of what we want to talk about. And then I'll speak about the integrated density of states for the discrete case, and then about the quantum graph case. Okay, so let me go through the introduction. So what we want to do is the integrated density of states is a crucial quantity when looking at random operators, and it is something like a normalized eigenvalue counting function. And we want to do this for geometric situations in Z to the D. I'll tell you in a moment what I mean by a geometric situation, but already here I would like to point out 2 points. So usually existence of the integrated density of states in random models is rather simple. It follows directly from an ergodic type theorem. And of course we could do this as well, but this result usually gives one kind of something about vague convergence of measures. And what we get here is a stronger result. We get convergence of the distribution functions with respect to the sup norm. So this is one important feature of our result, that we get a stronger notion of convergence, and in particular this allows us to deal with jumps of the integrated density of states which occur in various models. Actually, these jumps sometimes are known as scarce, and they have been mentioned yesterday in the talk of Schrader. I'll speak a bit more about this later. Let me give you a couple of examples of what I mean by a geometric situation. So one thing, for example, would be here. I mean, this is kind of a periodic thing. Think of it as being extended over the whole plane. So a periodic situation, and of course, periodic situations have been considered by many people, and in particular, this occurrence of scars in the periodic situations has been considered various places. There's work of Peter Kutschmann on this, and our results are close in spirit, though they are slightly differently formulated. There's work of Dodchuk, Matai, and Yates, this type, or even more general things. One could actually get away from periodic situation. One can do percolation models also, and that would mean that you go to each of these edges and you flip a coin, and depending on what you get out, you remove the edge or not. And if you do this, you may get something like this here. So that would be another type of geometric situation that we are interested in. And again, percolation, operators for percolation have been considered by various people. There is work of Ivan Veselic doing various things on this. Then there is work of Müller and Kirsch, and of Stallman and Kirsch, looking at finer structure and asymptotics of the integrated density of states. So this type of model. Of course, what you could also do is you could just do percolation on the usual graph z to the d, and you may get something like you see here. Again, edges are removed according to some probability law. And there's a third situation, which is not a random situation, but a deterministic one, which and this here, so this is the set of visible points on the two-dimensional lattice. So what you see here is what somebody will see who stands at the origin here and then looks around, and then he will be able to see certain points on Z2, and others will be hidden because he had seen some other points which are closer to him than the other ones. So this is the visible points of Z to the D. And that is completely deterministic, of course. This type of model appears in number theory, but it also appears in the study of disordered solids, though as far as I know, the corresponding random operators have not been considered so far. So what happens is then this type of model is a very good example, or rather counterexample, if you want to analyze disordered solids by diffraction method. So if you do some X-ray and want to find out something about disordered solids, then this type of model appears and gives you counterexamples to some assumptions, but I don't think that the corresponding operators have been considered. Anyway, so this is what I mean by a geometric situation. And all these situations have two things in common, which I will make precise in a moment. And one is somehow there is some finite valueness. Somehow locally you can see only finitely many situations. And the other is you have something like existence of frequencies. So if you look at a certain finite configuration, it will appear regularly in the sense that on the average it will appear so and so many times. And these two features are kind of crucial for our model and our results. Okay. So I think at this point I will leave the introduction and come to the second point, setting, and be more precise. So, how are we going to model this? So, what we are going to do is we will model these graphs or these geometric situations of Z to the D by actually attaching colors to the points of Z to the D, and the colors would kind of encode whatever geometric situation we see locally. So, definition, the following: we fix a finite set A, which we call the colors, and then an A coloring of Z to the D is a map which associates to each point in Z to the D a color in A. And a pattern is just a local version of this. So a pattern is a map which goes from some finite set Q in Z to the D to A. And then what we are going to do is we will identify patterns which agree up to translation. And just to make this clear, here I have a coloring. So it's a coloring by 3 colors, I think. It's blue, green, and red. And then, for example, what is happening here? Wait. Yesterday it wasn't there. So, okay, good. So the pattern is this one. It's red, green, and blue. And you see it here, red, green, blue, red, green, blue. So you see it 4 times. So all of them will be kind of identified. We say this is one pattern here, and you see it here, 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 and here. Right? So this is our, and then, as I mentioned already, we need something about regular distribution of patterns, namely existence of frequencies of patterns. And what we assume there is, well, first of all, we introduce the ball, or rather a cube or something. The cube around the origin with a side length 2k. This is this here. And then the frequency of a pattern is given if it exists. We just count how many times does P appear in omega when restricted to lambda k, and we divide by the volume of lambda k. So in our picture, that would just mean the following. Well, we put a large box around the origin here. We count how many times does P appear there. We divide by the volume, and we go to bigger and bigger boxes. And if the limit exists, we say this is the frequency of the pattern. And that will be essentially the only assumption we make. So we assume that we are given an A coloring, and we'll assume that the frequencies of all patterns exist. Right. So just to repeat this, So this is our basic assumption. We are given an A coloring such that the frequencies exist for every pattern, and all the examples I mentioned at the beginning, the visible points, the percolation model, the periodic things, satisfy this. And also, of course, whenever you have a random ergodic random process, then you will also have this property. So there are many examples of this. So this is the basic assumption. Let's put it here. Now we come to our operators. So right now, what we are roughly here. We have kind of discussed the setting, and now we will talk about the discrete case. So we'll introduce next the operators and then speak about their integrated density of states. So what are the operators we have in mind? Well, the operators we have in mind should include the discrete Laplacian, but they should also react to the patterns we see. And what we want is that they have two properties. One property is a finite range property. So as soon as 2 points are far and apart, the operator, the corresponding matrix element, will be 0. And the other property we want is a kind of covariance or equivariance condition. Namely, if at 2 places we see the same pattern, then the matrix elements should be the same. And we are going to make this more precise, but these are really the two things. So we consider operators from L2 of z to the d to L2 of z to the d, which have the property that they exist in R, kind of the radius, so that the matrix element AXY is 0 if x and y have distance bigger than R. So it's a finite range condition. And the other thing is the following. If you now look at 2 places, x and y, if you have an x here and a y here, and you see some pattern here, and now you go to another place, x plus t, and here you have y plus t, and here you see a certain pattern, something like that, and now here you see the same pattern, then you want that the matrix element is the same. That is an equivariance condition, and formally speaking it means, so the matrix element of x, y is the same as the matrix element of t plus x, t plus y, if omega at the ball or the cube around x with radius r, and union with this cube shifted by t is the same as what omega is at actually the shifted cubes, right? So it's really the operators react on the patterns. And these operators can serve as a type-binding Hamiltonians. For example, the discrete Laplacian would be an example, and of course the discrete Laplacian, together with a potential which only takes finitely many values, would also be an example. Now, if we are given such an operator, the next thing we need would be the restriction of the operator to a finite subset Q. So we take a Q finite and we say HQ is the restriction of H to Q. And so what this means is we just take we have the space little a2 of Q, and on this space we take just the matrix element which come from here. Sometimes this is denoted as Dirichlet boundary conditions. Never. So given this HQ, which is an operator on a finite dimensional space, we have the eigenvalue counting function NQ, which goes as follows. NQ of E is the number of eigenvalues of HQ which are less or equal to E. Right? So we have a finite dimensional space. So we can do this. Let's note it here. NQ of E is the number of eigenvalues of HQ which are less or equal than E. Right? Good. This is our eigenvalue counting function. And what we can actually also do is we could introduce some other finite dimensional Hilbert space and look at operators from Z to the D to this space H. But I'll not talk about this now. So now here comes our theorem in this situation. The theorem is as follows. So if I do this eigenvalue counting here, so and again I'm in the setting of my basic assumptions, so frequencies exist, then these functions, if I average them by the volume of Lk, converge for k to infinity to a function n, and this convergence is with respect to the sup norm. So, just to emphasize this one more, these functions, of course, are very much jump functions, right? I mean, this is a finite dimensional space, so typically this will look something like this here. So, and even though these are kind of rather jumpy functions, they will converge with respect to the sup norm. And that is the result here. And actually, more Moreholtz, we do have explicit bounds on the speed of convergence in terms of R and the convergence of frequencies. I mean, what we put in was that frequencies exist. This is kind of our assumption. If we know how fast the frequencies converge, and we know R, then actually we can say something about the speed of convergence. And that has a very interesting consequence, namely, if I look at the Laplace operator plus a potential, now the potential only takes finitely many values, then actually the speed of convergence will not depend on lambda. So we get uniform convergence, uniform in lambda actually. Why? Well, only the frequencies matter. The frequencies are not affected by this coupling constant lambda. Neither is R, the range of the operator. So we get uniform convergence in lambda in these type of models.
Can this limiting function n have jumps or not?
Yes, we come to this. Thank you. So we didn't talk about this earlier. Anyway, so if we now assume for a moment that we know a bit more, namely that the frequencies are actually all positive for all patterns which actually appear in omega. So a pattern either appears, then it appears with a positive frequency, or it doesn't appear at all. Then we can say two more things. One is that the spectrum of our operator is actually the topological support of mu. So what is mu? Well, we have this function here. It is the distribution function of a measure, and the measure we call mu. And the other thing is we can characterize the points of discontinuity of n on the integrated density of states. Maybe I should say this. So n is called the integrated density of states. So the points of discontinuity are exactly those points where we do have a compactly supported eigenfunction. So, and again, of course, if you are in a continuum model, you do not have these compactly supported eigenfunctions by unit continuation. These type of models, they can occur. And I think the first result of this type in a periodic situation was done by Peter Kutschmann. The formulation is slightly different, but this is really what happens. So in a non-periodic situation, I think this is in what we did with Peter Stollmann and with Steffen Klasser. We looked at quasar crystals, and we could prove this result. And then for percolation models, it was done by Ivan Veselic recently. Anyway, so we get this result here in this context. Yeah, thank you, Norbert, for your question. So it is really true that in these examples, there can be compactly supported eigenfunctions. And actually, whenever you have a percolation model, you will have quite a lot of them. And you can ask Ivan how many and where they are. So they do exist. Also, as an aside, I would like to mention the following. Somehow, these compactly supported eigenfunctions seem to be related to some notion of curvature on the graph. In the following sense, there is a notion of curvature, a very fine notion of curvature from Norbert Peyer-Imhoff and Oliver Bowers. And if you look at this type of curvature, you can show that if you have a planar graph or planar tessellation, you do not have compactly supported eigenfunction whenever this curvature is less or equal to 0. So negative curvature implies absence of locally supported eigenfunctions in the planar case. And this is something we did with Norbert and Peter Stollmann and Steffen Klasser. Good. Well, given that you have actually kind of this thing about the jumps here, you may ask actually how many eigenfunctions, how many locally supported eigenfunctions are there? And the answer is there are as many as possible in some sense. And more precisely, the following holds. This is something we are doing with Ivan Veselic. In the situation of the corollary, you can show that the compactly supported eigenfunctions span the whole eigenspace. So they are a basis. And that is actually much more generally true than this situation here. So yeah, we are working on how generally it is true, but much more generally. Okay, so let's put this here and say a few words on the proof. So the proof, as I mentioned already, is really something about ergodic theory, and it's a kind of a uniform ergodic theorem as follows. Well, consider functions f from the finite subsets of z to the d in a Banach space. Okay, and they should have three properties. They should be bounded, meaning if I plug in a set, the norm of the function, which is something in the Banach space, is smaller than c times the volume of Q. It is translation invariant, namely f of Q is the same as f of t plus Q, whenever omega at Q is the same as omega at t plus Q. And it's almost additive, namely f of the disjoint union of Qj's is the sum of f of Qj plus some boundary term. And then one can show that the function f is, if the function has these properties, it is almost additive, translation invariant, bounded, okay. Then the average is f lambda k divided by lambda k converged in the Banach space. Now you may wonder, okay, so what has this to do with what we did? Well, the answer is the following. If you look at these functions here, these distribution functions, they are members of a Banach space, namely the Banach space of right continuous bounded functions on R. And what you can show is that this thing here, as a function in this Banach space of right continuous bounded function of R, depending on Q, has exactly these properties. So the map Q goes to NQ is just a map which has these properties. So we can apply this ergodic theorem and get this very uniform convergence that we were talking about earlier on. So this is really the crucial ingredient in our considerations. Well, let's put it here, and let's now come to quantum graphs. So quantum graphs, of course, have been talked about very much during the last 2 days, so maybe I can go over this briefly. Of course, also random operators on quantum graphs have been considered by various people. So there's work of Eisenman, Sims, and Wartel on trees, and they could show persistence of AC spectrum. There's work of Post and Hislop, which could show actually localization for some tree graphs. There's also work on Z to the D on random models by Exler, Helm, and Stollmann, and they show localization. So here we have a kind of much more modest aim, namely we want to show uniform existence of the integrate density of states. So we look Z to the D as a metric graph by assigning the length 1 to each edge. ED is the set of edges, BD is the set of vertices. Well, we have the corresponding L2 space, the corresponding Sobolev space, and of course, for each function we get the boundary values of the function at the vertices. So whenever we have a G in the Sobolev space, we can look at its boundary values G of x and G prime of x, which is the function here. And the boundary condition is then a maximal subspace. Maximal is not visible, but meant or intended. It's a maximal substance L of Z to the 2D cross Z to the 2D, which has this property. So it's exactly what we learned yesterday, which was discussed there at length. I think actually Michael Kuwait told me that I should not talk about this at all anymore because these boundary conditions have been defined so many times so far. Anyway. Okay, good. So this is what we mean by a quantum graph. Now we want to do randomness, so we will introduce randomness, and we will actually introduce randomness in two places. One is we will have random potentials, but also we will have random boundary conditions. I mean, this is really what a quantum graph allows you. I mean, you can not only have potentials, but you can also have random boundary conditions. So we take a finite subset of L infinity, which will be our potentials, and a finite subset of boundary condition. Then a random potential is a map from omega in the product of these boundary conditions. So each of the potentials, each edge gets a potential, and it should be invariant. Namely, if I shift omega by gamma, gamma is an element of the translation Z to the D, or I could actually also speak about the automorphism group. And if I shift both omega and the edge, then I I don't get anything new. So I get V omega of V. And the same with the random boundary condition. So if I shift for each vertex, I get a boundary condition. If I shift everything, it remains the same. So then, given these two ingredients, I can define a family of random operators. Well, by saying the domains of definition, these are just all elements in the Sobolev space which have the property that the boundary values belong at the vertex x to the chosen boundary condition, and valid x by at the edge h by the usual Laplacian plus the potential. So again, randomness enters both via potentials and boundary conditions. And now we come to the result, and that is then also the last transparency. So the result is, assuming this situation, then we can do the following. We take any finite subgraph of c to the d, and we can define a function ne by saying, do the following. Take h omega, take the spectral family from minus infinity to e of h omega. So that is the characteristic function. So it's just the spectral projection from the interval minus infinity to e. Multiply this, so this is kind of a localization in the energy. Multiply this by the characteristic function of this finite subgraph. So then we get a trace class operator. We can take the trace and we integrate this, which depends on little omega, by our probability measure p. And we divide by the volume of the graph. And because we divide by the volume, this will not depend on the graph. So no matter which finite graph we pick, this thing in the end will not depend on the graph. And then the restriction we talked about earlier of our random thing, n omega 2 lambda k, convert with respect to the subnorm to a function n for almost every omega in omega. I mean, we are in a random setting. We cannot expect to have more than almost sure convergence, but this is what we get. And again, it's in the subnorm. And just let me point out the following. So n is unbounded, and little n is also unbounded, but the difference is a bounded function, so we can take the subnorm, right? So this is a phenomenon that happens here. We take the difference of two unbounded functions, we get a bounded function, and we can talk about convergence in the subnorm. We again have explicit bounds on speed of convergence. And again, we have our two corollaries. Well, the spectrum equals to the support of mu, and again, the points of discontinuity are those points where there is almost surely a compactly supported eigenfunction. Now, you can talk various examples we could talk about now, but I think I better stop here.
Can you use that under some second to conclude then that either you cannot have compactly supported solutions or you cannot have points of discontinuity?
Yes, yeah, it's an equivalence.
Equivalence, but what can you prove in that?
Oh, right. So I mean, so this is a quantum graph version. So there, I think it will be hard to get rid of compactly supported eigenfunctions. But if you manage this, then you will have continuity.
Yeah, okay.
Yeah. Okay. So let me stop here.
You mentioned briefly that you applied this to quasi-crystals, or you
Yes.
use quasi. Can you say a little bit more about the results that you obtained there?
Right. Actually, it's in some sense. So this is what we did with Peter Stollmann. We can also show uniform convergence of the integrated density of states. There, the models would be less random in some sense. I mean, kind of long-range order. But there, the situation is as follows. This long-range order would essentially also allow compactly supported eigenfunctions. So one very famous model, the Penrose tiling, would have compactly supported eigenfunctions. So you get the uniform convergence, but you also have compactly supported eigenfunctions. So, yes.
How strong is your assumption of existing frequencies?
Okay, so essentially it's a kind of ergodicity assumption. So as soon as you have some ergodicity in your model, you can show that almost surely the frequencies exist. And this almost sure existence of the frequency is exactly what gives you the almost sure omega here. So it's essentially, if you have ergodicity, you will have existence of frequencies, but also you can have existence of frequencies even if there is no ergodicity, like in the visible points. I mean, this example of the visible points, there is no real random process or anything, but you do have existence of frequencies. But so ergodicity means you will have this almost surely, but you can also have this in other examples. Yeah.
You said that you can have an estimate on the rate of convergence.
Yes.
If you know the estimates on, in particular, on rates of convergence to frequencies.
Yes, exactly.
Do you need to uniform convergence of frequencies? Or
No. So what we get
with
is
respect to the size of the project.
yeah. So what one does is, so one fixes one looks at a certain size, and then there are only finitely many patterns of this size. So as soon as for each of these the frequency exists, so up from a certain size on for all frequencies of this fixed size, you will be very close to your limit, and then you can operate with the patches of this size. Now, how do you choose this size? Well, this depends on some earlier considerations. So you do some considerations, then you get a size of patches, and then you work with these patches, but there are only finitely many. And
Let's thank the speaker again then.